All right. Hello, everyone. Welcome to the next FE review session by the CSVLB coveted by Theta chapter. We're going to be looking at some dynamics today, and we'll get right into it. We'll go for about an hour today, see what we can get through. Okay, let's take a look at the handbook as we do normally in the beginning. We have some common nomenclature of the different variables that we may see in these problems. We have particle kinematics, which is the simplest form of kinematics, where the velocity is the derivative of the position with respect to time, or time derivative, and then the acceleration is the time derivative of the velocity. So if you wanted to relate acceleration to position, you would say it's the second time derivative. We have velocity, instantaneous velocity, instantaneous acceleration, time, Cartesian coordinate system, RVA. And then we have also, you can define the derivative term for the three different motion types: position, velocity, and acceleration via dots. X dot can be referred to as the velocity, and X double dot would be considered the acceleration, each dot symbolizing a time derivative. Okay, I'm just going to skip to the next page, so just going to look at this first. We have radial and transverse components, a tangential sort of and normal direction. Actually, in this case, it's a radial transverse. I haven't seen very many problems use this particular system, but just know that if you had something at an angle and you wanted the radial and transverse components, you would be able to find them via these equations here in the handbook. We have particle rectilinear motion, variable A. If your acceleration is not constant, you can use these equations. But if it is, you can use these ones, which don't involve taking a derivative. Like, imagine this is if you had an equation for an equation for V, and you wanted to find the acceleration, you could use the derivative, take the derivative to get it. Otherwise, if it's constant, you can use these equations to get what you need. Curvilinear motion is very similar, only we have thetas instead of just a position. Thetas, angles, radiuses, radii. Okay, relative motion, a velocity of something relative to something else. So you can have that for every single type. It's explained in more detail right here in this graph. The velocity of A is equal to the velocity of B, or position of B, in this case vector, plus the velocity of A with respect to B. And that can get you the triad relationship. And you can do the same in rotational coordinates as well. Circular motion, similar to rotational motion, radial and transverse components as well. But then we have an arc length S in addition to a theta, which you can get the arc length if you turn your theta into radians and you do r theta, which is explained right here. What we will see in some of the problems we're going to do is radius normal and tangential components of a particular value. In this case, could be velocity or acceleration. You can find the tangential component via you can find the tangential, let's say, acceleration, which I believe is r alpha, and then r omega will get you the velocity, tangential velocity. I'm not sure why they don't. Actually, no, it's right here. V squared over rho, which they use rho here instead of r. It's the radius of curvature. So in this case, wherever the center of rotation is, it's going to be from that position to the object that's moving or the path that it's moving on. If you take the tangential velocity divided by that value, you will get the normal component of the acceleration. Yeah.
Good old dynamics.
What about it?
Good old dynamics.
Yes, indeed. I'm not really sure why it doesn't give you directly what the tangential is. It uses this unit vector E, T. But from what I've seen, you can get the tangential, at least tangential velocity in R omega. And normal would be R alpha, or yeah, R alpha. Okay, it has it up here, those two equations up here for the radial transverse, but for some reason it's not here for normal tangential. I believe they're very similar in that case. Constant acceleration equations, these may look familiar. You can get them by deriving something from acceleration all the way up into a position. Free falling is an example of this. Constant acceleration for angular equations look similar, only the values are in rotational motion terms. Projectile motion, you can, if you're not comfortable with deriving the equations when you're solving the problem firsthand, you can look to these to help you out. Non-constant acceleration, have some integrals here of tau. What is it considering tau? Maybe, oh, it's time. It's just a fancy time. Okay.
Yeah, it's like a, if I remember correctly, I think it's time in a different domain, I think.
Yeah, yep. Weight, pretty sure we all know the definition of weight. It's cool. Particle kinetics. So if you're not dealing with like a rigid body, which is definitely a dynamics topic, you do your sum of forces about this particular particle and you equate it to a mass times acceleration. So if you were here in the statics lecture, if you look at this one, it's a little different. Sum of forces, it would be equal to 0 in a statics problem. But here, since we're doing dynamics, you equate it to a mass times acceleration, which is a force. Constant mass allows you to simplify some things here. Normal tangential kinetics for planar problems. Work and energy is another important thing. And total energy, conservation of energy relationship right here. Kinetic plus potential equals kinetic plus potential from two different states. And if it's non-conservative, then you're gonna, well, it's gonna be a little more complicated. Work from, this is a, yeah, kinetic in state 2 plus potential in state 2 is equal to kinetic in state 1 plus potential in state 1 plus work it took to get from state 1 to state 2. Work done. Kinetic energy here for a rigid body, it has a moment of inertia with an angular velocity in addition to 1/2 mv squared. And this is particularly, you see the C here, the velocity at the center of mass with potential energy, which is fairly simple. MGH, or galactic, which is Ks, or 1/2 Ks squared when you use it in energy form. Work, so force times a distance. Force applied upon a distance, over a distance. You have a spring, weight, constant, variable force, power, and efficiency. Power is derivative of work with respect to time, time derivative of work. And it's fairly simple to get that. Impulse and momentum. So yes, you can see dynamics has quite a few topics. So we unfortunately will not be able to go through each and every one in terms of the problem, but we'll be able to get through a couple. That hopefully should give you an idea of what you should expect. Then there's a momentum method, and there's a impulse method as well, which are detailed here. You can look them up. And then we get into friction. the frictional force on the object will be equal to the normal force multiplied by the coefficient of friction. And then as we get into rigid bodies, we stop looking at particle systems and we start going into some more complicated differential of mass that we have to apply over a body. Instantaneous centers is a really nice way to analyze rigid bodies because it allows you to figure out all of the details in terms of accelerations and velocities, angular and linear, by finding the center of rotation, which you can do by extending the bars of your system and finding where they intersect, and where they intersect with the instantaneous center of rotation. For here, for 3 and 2, they happen to intersect literally at the joint where the bars are. And with that, we find this instantaneous center of rotation right here. We also find one where bar 3 extends into the vertical axis of the spin. Same with 2 with the vertical axis of the block. And so with those, you can relate the velocity of different parts of the system to each other and solve for what you need. Kinetics of a rigid body, we have forces ma, center of mass, sum of moments, we have alpha, and then we have a rho alpha. A mass moment of inertia as well. Integral of r squared is differential of mass. Can be a little bit difficult to calculate. Equations of motion for each of those particular things, mass moment of inertia for different dimensions, and parallel axis theorem, which is nice, which we used in statics. You can use it again here for moment of inertia, using in the exact same way. And then the radius of gyration is the relation to the moment of inertia. You can also do angular impulse and momentum methods on rigid bodies as well, which is what this is detailing. And now into vibration, which we will not be getting into today. Those of you who study at CSULB, I don't believe there was a particular section. There was a section on vibrations, but I don't think the curriculum normally gets to it. So, well, as you can see, it's a fairly small section too. Which, note to everyone, they did want to include a larger vibration section on the main exam. So that might be something you might want to look into and learn a little bit more about, even though you didn't have formal education in it. And at the end, we have a list of all of the mass centroid, a moment of inertia, radius of gyrations of different shapes, which is likely going to be where you're going to be finding all your equations for different problems. Right, and that should be the end of this section. It is. Let us get to some of the problems. Let me actually erase the current work that I have done so it's not spoiling the fun. And we'll get into that. I did solve these ahead of time, so I am familiar with them when I go over them, so we don't waste time. I don't waste time trying to figure out how to solve them. All right. Some of these are fairly straightforward. Some others may require some intuition. But I'm pretty sure we all got that. I had a bigger eraser, so it's kind of small. All right. Let us begin. Is this visible for everyone?
Mm-hmm. Yes.
It's large enough. I can make it larger.
That's
Wide.
good.
Does this make it bigger?
Yeah, a little bit.
Okay, just so I have enough writing room. Okay. So let's look at this first problem. A particle's curvy linear motion is represented by the equation S of t is equal to 20t plus 4t squared minus 3t squared. Okay. What is the particle's initial velocity? Any takers for this problem?
So we have a st. So if I'm not mistaken, if we take a derivative, we should get velocity, correct?
That is correct.
And then if we're talking about initial, that should be at time equal to 0.
So we can set t equal to 0, right?
Mhm.
For the we're gonna have this is what we're gonna be looking at, which is gonna give us 20. Does everybody understand that? You take a derivative, this t is going to be removed. This is gonna turn into 8t, and this is gonna turn into, did I miss one? That's a cube. 9t squared. The two terms that have t's will go to 0 due to t being 0 when you take the derivative. So we're going to be left with just 20. And so 20 is going to be the initial velocity. It's going to be v equals to 20. We have an answer choice 20 here. So that was pretty straightforward. You just have to know the relation between position and velocity. All right, let's look at the next one. We have a projectile with an initial velocity of 110 meters per second and a launch angle of 20 degrees from the horizontal, assuming that the surrounding terrain is level and air friction is to be disregarded. What's the flight time of the projectile? Let's first draw a little picture. We have some looks like this. We have something launched. Doesn't tell us where it's launched from, if it's launched from ground level or not, but we'll assume it is.
We can make some assumptions here.
110 meters per second. This is 20 degrees. We want to know what the flight time is. How can we do this?
Like,
we need to find out how long this ball is in the air, right?
Yeah.
The x dimension won't help us with that, will it? The x velocity is going to be constant throughout this whole flight time. That's not nice. Well, not nice for us trying to figure out how long it's in the air.
No.
So what we can do, why don't we look at the y, not forces. The velocity in the y direction.
Velocity in the y, and then my guess after that would probably be take an integral of it. But we wouldn't know how far it is. Never mind. Let's just.
So what's the velocity in the y direction? How many components we have?
It should be 110 times sine 20.
Yes. That's one. What's the other one? This is the velocity equation. So if you remember, if a of t equals a naught, what is let's say a y of t equal to a naught, which is what, 9.81? What's v y of t?
A y of t equals a naught. So if we're looking,
right?
Yeah.
So vy is going to be 110 sine of 20, but we have to add this term, don't we? Which is negative because we have a negative acceleration due to gravity. Right?
Okay.
So we can solve for t here, right? If we set this equal to 0, so what we're doing is we're finding the point where the velocity in the y is equal to 0. So that would be the peak. Set the derivative of the position, right? Sorry,
Oh,
yeah, the derivative of the position, which is the velocity.
okay.
Equal to 0. That's how you find a maximum, is it not?
Yeah. Should okay. So that means
Right?
okay, yeah. Yeah, you get the 3.8 right, yeah.
So we got the time it takes for this thing to get here. Nice. Well, we're halfway there. We want to find out how long it takes to get here.
Mhm.
So, considering the acceleration is constant, what would be the time for it to get over here now that we know this time? We know the time it takes to get from here
Uh-huh.
to here is 3.84.
Yeah.
Now from here to here, what do you think that time is?
See, my simple brain wants to say that it would just be the same time
Right. Why is it you think that?
because we found the time for half of the path. So if air resistance is not accounted for, I don't think the velocity has changed that much. It's because acceleration is constant, right?
Mm-hmm.
So I don't see the velocity changing then. It should still be the same amount of time. At
And
least
you'd
that's
be
what.
and you'd be correct on that. That's exactly how it is. So
Right.
t total time it takes is going to be 2 times 3.84, which is about 7.67 seconds. I say 7.7. Mm-hmm. Would be it. You just use the derivative of the acceleration in the y direction. You get t in terms of Vy, and you set Vy equal to 0 as you reach the peak, and you multiply your result by 2. Yeah. Flawless. Again, these are kinematic kinetics problems. This one deals with friction. Well, I guess I left my things in there. Well, that's fine. We have a 52 kilogram block starting from rest position, and it slides down an inclined position to B. Coefficient of friction is 0.15. Okay, so you want to find the velocity at the block over here. So as you can imagine, we're likely going to be using another one of those equations we've used before. But which one? We'll find out. Where should we start? You can see I've already noted down what those two things are.
Yeah, taking into account weight and normal force.
Mm-hmm. We know that's what the force of friction is going to be. We know weight is going to be mg sine theta. And we know this is going to be, we know the normal force is mg cosine theta. And we're going to have a mu for the friction. All right, cool. We have those defined. That's nice. We know what theta is going to be.
It's 12. Okay. Oh, wait, is that? No, it's not.
Right.
Probably.
Which is fine. I don't know what that is. Doesn't matter right now. We're just setting everything up.
Yep.
Cool. Now, what else do we need to know? What value do we need to get a velocity? What needs to be known about this block coming down in this direction?
Distance traveled?
Well, we know that it's 20.
Right. Okay.
Another thing I should have mentioned is if we set we are setting our coordinate system to be like this.
Oh, right.
Well, I mean, we can still call positive to the left, that's fine. That doesn't matter too much, but we're doing that so we don't have to cosine this 20.
Right.
But we can sum the forces in the x direction, can't we? Summing the forces in the x direction. What does that have to be equal to? Mass times acceleration in the x direction, or max, as I like to call it. So what is the sum of the forces in the x direction? Force of friction plus or minus the weight. Or actually, plus or minus force of friction plus or minus the weight. Which ones are positive, which ones are negative?
Well, we're defining that x to the left is positive, correct?
Yep, and you know the friction force would go this way.
All right. So that means it's got to be negative FF plus W.
Yeah, I agree. So we have mg cosine theta times mu minus plus mg sine theta divided by m equals ax.
And the ends are just going to go away. We don't care about that.
Exactly. The whole thing is that once we get ax, what we can do with that is use it in an equation we can use to instantly get that final velocity. Because once you know the acceleration, it's constant, you can get the velocity from that. Same thing if you know the velocity and time, you can get the acceleration. Okay. If we do some math here, we'll get that ax is equal to 2.415. That looks pretty messy.
I guess I did the math wrong then.
What did you not get that?
I got 5.13.
5.
5.81 times cosine of 10. Yeah, that's 22.62. 22.62 times mu, which is 0.15. Okay. 9.1 times sine of 22.62. Yeah, and then we have to add those. Oh, wait, that's negative. Never mind.
Yes, it is negative.
Forgot about that. Yep, you get about 2. I got 2. Yeah, about 2.415. That is correct.
Cool. We can get the velocity at position B via this equation. Well, yeah, it's going to be squared, but it's going to be V initial squared plus 2 times that constant acceleration, initial acceleration, times the distance that is traveled.
Okay.
We know this distance, we know this acceleration, we know this velocity, so we can get our velocity at B, which is the final position.
Okay.
VB is the square root, this is 0,
Right. Let's start
square
from
root
there.
of 2 times 2.415 times 20, which I think is like the square root of like 90 something.
Yeah, it's 9.83. So it's D.
Yep, it's like it's D indeed.
We had this during dynamics.
What's
Like
that?
the actual. I wish we had this during the actual dynamics class I took.
I know, right?
This actually makes sense. I don't want to talk crap or anything, but Momenty didn't make it easy.
No, well, these are not some of the most difficult problems. we do have a couple. The last two are kind of involved, which we'll get into, but we have two more before we get there.
Okay.
Like this one. This one is fun because it looks like it could be really complicated, but if you know just one equation, it's very simple. I don't even know if I mean, I can tell you what I would do to go about it the way if I didn't know this equation, but you have something you have this heavy car, okay? Heavy car. And it's towing something that's also heavy. We have a friction, it's moving along a curved road. This thing has a radius, this curved road has a radius here of 200 meters. We have a coefficient of friction equal to 0.80. And it's traveling at 100 kilometers per hour. What is the banking angle required such that the tire friction will not be necessary to prevent skidding? Okay, well, if you read this incorrectly, you could also make it much more difficult on yourself. This last statement, such that tire friction will not be necessary to prevent skidding, it's saying what is the banking angle so that you don't require this friction to play any part in preventing skidding? So that says don't find the friction force. Find the banking angle that will accommodate for this speed, this load. Actually, I think it's even just the speed and the radius. I don't think the load has anything to do with the answer either. So to get the angle, just an equation for the, I was not able to find this equation in the handbook. So it might not be in there, which means you might not see a problem like this, but it's a good equation to know regardless because it's the equation for the banking angle of anything with a velocity that's under the spell of gravity with a particular radius. This is literally the equation, and you use 100 times 1,000 divided by 3,600 to get us into meters per second, which is squared, divided by 9.81 times 200. Which gives you about 21 degrees if you do the arctangent of that. So very easily you're able to solve. Didn't care about how heavy it was, did not care about the friction coefficient either. It's literally just have that equation, which apparently for some reason is not in the handbook. I don't know why that is. Maybe I have some outdated problems, but you just needed that equation to do it. And if it wasn't in the handbook, if you searched up banking angle and it was there, it's a simple equation that you could do just by looking at it. So even if you were confused about it. So it wasn't too bad, huh?
No.
But again, it required you to know an equation, which is not always fun.
It is not in the book.
Yeah. I've checked too. All right, so we go on to the next one. Why does a spinning ice skater's angular velocity increase as she brings her arms closer to her body? Is it because her mass moment of inertia is reduced, the angular momentum is constant, or her radius of gyration is reduced? Or all of the above? What do you think, Mr. Cameron?
Let me think this one through a little bit. Get some definitions.
Angular velocity depends on what? In terms of the stuff that's there. How does it relate to the angular momentum and mass moment of inertia?
We
Remember, what's the thing that we know about momentum? There's a thing called conservation of momentum, right?
yeah.
So in
Kind of like,
conserving momentum, we know that one has to be true.
okay.
And if we know the equation, we'll be able to find it in the handbook. There's an equation:
Angular. Yeah, that's what
angular
I was
momentum
looking
divided
for.
by the mass moment of inertia is the angular velocity. And we know that this momentum cannot change. So what does that mean about this? If this increases, what has to happen to I? It has to
Yeah.
decrease.
Yeah.
So we also know that that's true. And by this point, you're like, well, two of them are true. So
which
D
one's
must be the answer, which is right. And if you also look at the equation for the radius of gyration, which I don't know off the top of my head, but is in the
I
handbook.
think it's I over or root I over n. I think or I over
Yep,
n.
I
It's the
over
radius
N.
n.
So
Yeah.
if I goes down, the radius of gyration will also go down because I is being reduced.
Right.
So
Okay.
they're all true. True, true, true. So we get D, all of the above. And yeah, there you go. Cool, huh? I like those questions. They're easy to guess right if you don't know about them.
Yeah. You just need to know the equation.
Okay, now we have our instant center problem. In the linkage mechanism shown, link AB rotates with an instantaneous counterclockwise angular velocity of 10 radians per second. What is the instantaneous angular velocity of link BC, which when AB is horizontal and CD is vertical? Just reminding you of kinematics.
Yep.
Exactly what it is. So we're going to have link B that I'm going to draw carefully. B and C. We know the length of it is 5 meters. And we know it's at an angle of, at 3, 4, 5 triangle. All right, do you remember how to use instant centers at all?
I remember graphically because I
Okay,
tutor it
what do
every
you
now
do
and then.
graphically?
Okay, if I remember correctly, there well because when we learn from Razai, you got to start with the circle, and you have to label each one of your links.
Mhm.
I believe 1, 2, 3, 4. Connect the ones that are already connected, like 1 to 2 is at AB, I believe.
Like if you do this,
Yeah, something along those lines. And
and
then
then
you have to,
this is IC, right?
yeah, that's from like, yeah,
This one is extra simple because it basically tells us, oh yeah, keep CD vertical and AB horizontal, which
Mhm.
kind of just makes the whole things IC right here.
Yeah,
So there's not going to be an IC, like if let's say we extend B over here, there's one here as well.
yeah, no,
And B this way, there's also one over here, but we're not going to be using those. We're going to be using this one
Mhm.
because we have information over here, right? We have angular velocity, angular AB, which is connected to this. So if you remember your angular equations, if we have an angular velocity and a radius of action, we actually can find the tangential velocity here, dB, which is nice because we need that.
right,
Because we need to take what we know here at AB and relate it as far over to the right side as we can to try and find information about BC. So angular velocity is equal to what? R dB?
yeah.
Am I correct on that? I'm not. Other way around.
Or is it?
It's VB equals to R. It's R omega.
Okay, yeah, and then you can find um, VB here because you have the length of
Yep.
AB, so you can find VB.
meters per second. Yep. Now we need to find omega BC, which is going to be equal to
Is it
VB divided by R. But what's R?
isn't R IC, the length of IC?
Yep.
Yeah.
We know this is this length due to this triangle here.
Yeah.
We know that's 4. So the distance from B to IC is 4.
Divided by 4. It's most closely D, unless there's another part that we have to do, but I don't think so.
That's it. Mm-hmm. This one was seemingly simpler since it didn't kind of give us too many instance centers to work with. I thought it was a nice problem because it reminds you how to use instance centers simply and how to relate angular velocities through instance centers.
I always liked instance centers in kinematics.
Yeah, they were fun. They were a lot easier than the very long equations of, deriving the
vector loop equations for everything.
Vector loop equations.
And once you got to acceleration, each aspect had like 4 different components, so it was
exactly, and you had to do a long equation to get them.
That was fun. All right.
None of that is present here, fortunately.
No, and I would highly doubt that you would see something too complicated like that on the actual FE because you only have a certain amount of time.
You have about 3 minutes per problem.
Yeah, so I don't think they're going to give you like the problem that's there's a 6 linkage.
Right. I mean, they could give you a long problem, but it's up to you to recognize whether it's long or not.
Yeah,
And see if there's a shortcut you can take. A lot of them have shortcuts that if you can find them, you can take advantage of them and solve them with very little calculation.
All right.
This one you have what? You have one calculation for VB and a second one for BC.
Yeah, omega BC, and then you're done.
Yep. Okay, so the last one I currently have for y'all. Using some energy theorems now. There's a 40 kilogram mass guided by a frictional spring constant is that, and it's compressed sufficiently and released such that the mass barely reaches point A. All right, what do we know about this system? What is the initial spring compression? We want to find X. If you know F equals Ks, we want to know S, or 1/2 Ks squared, we want to know S. So we know that the bottom of this system, right, is going to have a particular energy. And due to the conservation of energy, we know that the top is also going to have the same energy. So how do we relate those two? What's the energy of the bottom?
Energy. Oh, they gave us some. Oh no, that's K.
What is EA? No, you don't need a particular value. Just give me the expression for it, the equation. Energy down here at A.
Yeah, I'm looking for an equation under energy.
It's not too complicated if you remember. Just remember Whistler's class, and be like, hey, I can take a derivative.
I try not to think of Whistler's class when I'm not in it. Listen, it's Friday. I only have to think about CCS and meeting with my boss.
True. Anyways, well, look at this. Right. Isn't this not the energy right here that I wrote to the bottom part?
I was looking at something like that. Where was it? Right.
And S is our unknown variable. And then we have EB. What's EB? What's the energy at EB? At B sum.
I feel like we have to relate it to like the height or motion, you know?
Yeah, what's its potential? Its gravitational potential, isn't it? MGH.
Yeah, yeah.
So if we equate, since we know EB is equal to EA, we can have 1/2 KS squared equals to MGH. What the? Not sure what happened there. And we're looking for S.
Okay.
So we can have S equals the square root mg 2 MGH over K. That 2 MGH looks familiar, doesn't it?
Kind
It's
of.
2 MGH minus the K is, well, actually, I think actually still including the K, is the distance that the spring, you have to stretch a spring for it to reach a particular height, H, with spring constant K. It's a little bit of a standard formula if you do fluid mechanics. I believe it's also present there
I
with
kind of remember that
fluid potential.
MGH from fluids.
What's that?
I kind of remember that from fluids.
There's a lot of MGH
Yeah.
in fluids.
Yeah.
Potential energy is pretty
Yeah.
key. Just get that pressure.
Yeah, a lot of it was used for pressure. Stuff like that.
Mm-hmm.
I got about 1.35, so I'd say rounding up 1.4.
Yeah, that's it.
Cool.
Got it. Good to go. We have a little bit of time. Let's see if I can find a problem in this book of stuff. Fluid mechanics. We're not doing that yet. That's on the Halloween. What's it called? Hallow Eve. Hallow Eve. Pressure vessels.
Coming up soon.
So it is coming up soon. Dynamics. What are you? Dynamics. That's not that. Thermodynamics. That's not what also incorrect. You know, by the time I find something, it's going to be time. Does this not have dynamics? Oh, here it is. Gosh, it was way at the end. It's so far away from statics, I was confused. Okay. Kinematics, rotational things, kinetics of rotational motion. Oh, it has the problem I just did. It's a nice complex one. Most of these are not too complex, actually. Energy in the work. Let's do this one. All right. 2 kilogram, why they use 2 twice blocks. I'm gonna draw like an L-shaped thing. We have block. Really don't want to change colors? Okay, fine. Block A and block B that are connected by a linkage. Totally accurate linkage. I can draw fine.
Yeah, that's fine. Okay.
It's at an angle of, that's totally a straight angle. Drawing virtually is rough. 30 degrees, the length of this thing is also 3 meters. This speed of this guy is going 3 meters per second. Okay, hopefully that's visual enough. 2 kilogram blocks. kilogram. M equals 2 kilograms. Assuming that the surfaces are frictionless, what is the velocity? We want V of B. If A is equal to 3 meters per second. All right, we have to relate stuff here. What should we do? What should we do?
Okay, so that means if I remember Momeni's class, there's that equation, that relation VB is equal to V. What was it?
VA over something equals VB over something else, right?
It was like one velocity equal the other velocity plus or minus. I can't remember exactly.
It's,
the velocity relative.
Angular velocities of both are going to be the same. So you get the tangential of A and tangential of B over what? Something we don't have yet. We need to get the instant center.
Okay.
If we get the instant center, we extend these both this way. We get a new point. So this point, let's call it C. AC and BC. This is what's the instant center is the way we relate the two. So this is going to be AC, and this is going to be BC. We need the distances
of AC and BC.
Of these two. Correct. And how can we do that? We have a 30-degree angle here.
And we have the 3 meters. So
what's BC going to be? BC.
Sine of 30 equals, BC, sine of 30 equals opposite over hypotenuse.
So this is 30, right?
Yeah, so we go sine.
BC
30.
is going to be sine of 30. No.
Yeah. Opposite over hypotenuse. So it should be, right? It should be sine of 30 times 3, right?
Did I write the angle incorrectly? I think I did. I think that's not the 30. That's not. The 30 is over here. This is the 30. Does that make sense?
Oh, yeah. Okay, that actually makes a lot more sense.
Yep.
Yeah. So then it'd be cosine of 30 times 3 adjacent over hypotenuse. So that's about 2.5, 2.6.
Mm-hmm.
And then the sine is 1.5.
So we can get VA times BC. Divided by AC equals VB. So VB is 3 times cosine 30 over sine 30. What's that ratio?
Oh, okay. I just got the full answer. Yeah.
Is it 5.2?
Yeah, 5.2.
Yep, that's it. Answer choice. Well, you have obviously 5.2 is there, but yeah, it would be D. Yeah, another instant center. Way to go. So if you see two rigid bodies, at least all the problems in here are instant centers except for 2. Number 7 and 9. Number 7 uses mass moment of inertia. Moments about the center of gravity. We got 5 minutes. Let's do this one really quick.
Okay. I have a meeting at 12 too, so.
Oh yeah, you can head out if you need to.
Okay. Yeah, I'm gonna get ready for that meeting.
That's okay. Actually, I just can't hear them. That's fine. That's cool. We cool.
Okay.
What the heck? Okay. Thank you everyone for joining us today for this little short session. Hopefully it was useful. If you have any questions, please again contact us. We have a Discord channel. Join up on it, and we'll be happy to help you out. All right. Thank you everyone. Take care.